Let's travel into the future. What will we see?
I could sit there all day. You could sit there for a month and postulate at what the effects of the world switching over to thorium energy would have been. It's almost unfathomable.
I think it's always been the right time for thorium. I think it's been the right time ever since the research was canceled in 1974. The United States would have probably achieved energy independence around 2000. Our fossil fuel usage would be diminishing every year.
You wouldn't have nuclear waste issues like we're facing today. Fukushima wouldn't have happened. 3 Mile Island wouldn't have happened.
We would be producing continually less and less carbon dioxide emitted to the atmosphere per year. Oil consumption would be on the decline. Environmental quality would be on the rise. We would be in a very different situation now, and it could have happened.
The great tragedy is it could have happened, a third of a century ago.
That's the part that I find almost so tormenting, is that was a very realistic future that could have taken place. We don't want to wait any longer for that future.
In the 1950s, the scientists who created the atomic bomb offered a promise. By splitting the atom, we could have a limitless supply of electricity that could end pollution and bring peace to the world forever. But after the disaster in Japan, that dream has never looked more like a nightmare.
I think it's going to be a tough road for nuclear power, given the events in Fukushima. Let's face it, this is the first time we've ever seen a nuclear power plant literally explode.
Today, as the world grows increasingly desperate for clean energy, a new breed of engineers and energy geeks says we need nuclear power, now more than ever. 50 years ago, a forgotten government experiment seemed to prove another kind of nuclear energy could nearly eliminate the risks of meltdowns, waste, and weapons.
In other news, an obscure metal that could energize our world. It's called thorium. It's eco-friendly, and there's lots of it.
The amount of thorium that it would take to provide all the power to run your entire life is about the size of a marble that big.
The Chinese are investing millions in research into reactors powered by the element thorium, a metal proponents say as common as lead.
It's like, dude, what have you been smoking? No one thing can do all that. It can't make energy and be clean and help with space travel. You do feel a little bit like, an evangelist when you're talking about this stuff.
Did the United States abandon a brilliant idea in order to build bombs?
Thorium is very, 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 very good for our environment, and there'll be another video I'll show you. This video is from Motherboard TV, titled The Thorium Dream. Okay. So I'm gonna go to Thorium and Energy Solution, Thorium Remix 2011, uploaded by Gordon McDowell. The first 5 minutes of the video
It's unhappy.
will explain.
The heavy water reactor will use about 0.7% of the uranium's energy value, and the light water reactor will use about half of 1%. They both do terrible. At normal pressures, water will boil at 100 degrees Celsius. This isn't nearly hot enough to generate electricity effectively. So water-cooled reactors have to run at over 70 atmospheres of pressure. You have to build a water-cooled reactor as a pressure vessel. The number one accident people worry about, pressure is lost. Water that's being held 300 Celsius flashes to steam. Its volume increases roughly by a factor of 1,000. If you don't get emergency coolant to the fuel in the reactor, it can overheat and melt. This is what drives the design of this building. So if this happens, all the steam is captured in this building. Now the reactors we have today use uranium oxide as a fuel. It's a ceramic material, chemically stable, but not very good at transferring heat. If you lose pressure, you lose your water, and soon your fuel will melt down and release the radioactive fission products within it. So they have a series of emergency systems designed to always keep the core covered with water. We saw the failure of this at Fukushima Daiichi. You know, they had multiple backup diesel generators, and each one probably had a very high probability of turning on. The tsunami came and knocked them all out. And people sometimes say, is nuclear energy safe? And the first thing I say is, well, which one? Thousands of different ways to do nuclear energy. I'm saying, is the car safe? Well, which one? I had the good fortune to learn about a different form of nuclear power, the liquid fluoride thorium reactor.
We can fully burn up the thorium in this reactor versus only burning up part of the uranium in a typical light water reactor.
It's not based on water cooling, and it doesn't use solid fuel. It's based on fluoride salts as a nuclear fuel. You have to heat them up to about 400 degrees Celsius to get them to melt, but that's actually perfect for trying to generate power in a nuclear reactor. Here's the real magic. They don't have to operate at high pressure. They don't have to use water for coolant, and there's nothing in the reactor that's going to make a big change in density. Unlike the solid fuels that can melt down if you stop cooling them, these liquid fluoride fuels are already melted. In normal operation, you have a little piece of frozen salt that you've kept frozen by blowing cool gas over the outside of the pipe. If there's an emergency and you lose all the power to your nuclear power plant, the little blower stops blowing, the frozen plug of salt melts, and the liquid fluoride fuel inside the reactor drains out of the vessel, through the line, and into another tank called a drain tank. In water-cooled reactors, you generally have to provide power to the plant to keep the water circulating and to prevent a meltdown. But if you lose power to the Lftr, it shuts itself down all by itself without human intervention.
A staggeringly impressive level of safety, even if there's physical damage to the reactor.
Thorium is a naturally occurring nuclear fuel that is 4 times more common in the Earth's crust than uranium. It's so energy dense that you can hold a lifetime supply of thorium energy in the palm of your hand. We could use thorium about 200 times more efficiently than we're using uranium now. Because the Lftr is capable of almost completely releasing the energy in thorium, this reduces the waste generated over uranium by factors of hundreds and by factors of millions over fossil fuels. We're still going to need liquid fuels for vehicles and machinery, but we could generate these liquid fuels from the carbon dioxide in the atmosphere and from water, much like nature does. We could generate hydrogen by splitting water and combining it with carbon harvested from CO2 in the atmosphere, making fuels like methanol, ammonia, and dimethyl ether, which could be a direct replacement for diesel fuels. Imagine carbon-neutral gasoline and diesel, sustainable and self-produced. You can see that uranium-235 is like on par with silver and platinum. Can you imagine burning platinum for energy? And that's what we're doing with our nuclear energy sources today. We're burning this extremely rare stuff, and we're not burning thorium. You know, some people are kind of environmentalists, and they say, listen, nuclear power is not sustainable. We're going to run out of uranium. Okay, I will yield that point to you if we're talking about today's nuclear technology. In 2007, we used 5 billion tons of coal, 31 billion barrels of oil, and 5 trillion cubic meters of natural gas, along with 65,000 tons of uranium to produce the world's energy. So I have a friend who's trying to start a rare earth mine in Missouri. Jim, how much thorium do you think you'll be pulling up a year? He goes, I think about 5,000 tons. 5,000 tons of thorium would supply the planet with all of its energy for a year. And he goes, and there's like a zillion other places on Earth that are just like my mine. It's a nice mine, but it's not unique. It's not like this is the one place on Earth where this is found. Every time mankind has been able to access a new source of energy, it has led to profound societal implications. Human beings have had slaves for thousands and thousands of years. And when we learned how to make carbon our slave instead of other human beings, we started to learn how to be able to be civilized people. Thorium has 1,000,000 times the energy density of a carbon-hydrogen bond. What could that mean for human civilization? Because we're not going to run out of this stuff. We will never run out. It is simply too common.
Okay, now I'm going to show you another part of the video about 111, where they can talk about how much we need thorium and why we're running out of rare earths.
Ozone and particulates from coal-burning power plants kill 60,000 Americans. Clear right now, Earth children have some level of permanent neurological impairment, probably estimated a permanent IQ loss in those kids of 5 to 7 points. There are now 640,000 children born in this country every year who've been exposed to dangerous levels of mercury in their mother's wombs. Ozone and particulates from coal-burning power plants kill 60,000 Americans a year. 1 million asthma attacks, 1 million lost work days every year. You know, that's part of the cost of coal that they don't tell you about when they say, oh, it's only, 10 cents a kilowatt hour.
Both light water reactors and CANDUs do not use very much of the energy.
That you could take it out on the battlefield and use it, and then when you leave it for the host nation, and they run it.
Prosperity is related to energy. If we can bring people to about 2,000 kilowatt hours per year of electrical energy, they have a chance at achieving prosperity. Now, of course, prosperity depends upon the rule of law, good government, property rights, education. But electric power for heat, light, transportation, safety, and so on is a critical element of prosperity today. Developing countries know this. Energy and coal use is growing rapidly in all the developing countries. They want to achieve that level of prosperity, and they're being supported by Peabody Coal.
The National Academy of Sciences said that every freshwater fish in the United States of America now has dangerous levels of mercury in its flesh. And that mercury is coming from coal-burning power plants. My levels of mercury came back 10 times what EPA considers safe. I was told by Dr. David Carpenter, who's the National Authority on Mercury Toxicity, that a woman with my levels of mercury in her blood would have children with cognitive impairment, with permanent brain damage. I said, "Oh, you mean she might have?" And he said, no, the science is very clear right now. Her children have some level of permanent neurological impairment. Probably estimated a permanent IQ loss in those kids of 5 to 7 points. There are now 640,000 children born in this country every year who've been exposed to dangerous levels of mercury in their mother's wombs. Ozone and particulates.
The real challenge was spent. They say, what's the concern? Well, the actual fission products, that's what happens when you fission the stuff. Then there is what's called the transuranics. That's what happens when the uranium absorbs the neutron and doesn't fission. It turns into plutonium, americium, and curium, and a few others. Most of it's plutonium. I mean, the overwhelming majority of transuranics are plutonium. So when you talk to people about waste disposal, they say, what's the concern? Well, most of the stuff that's in the fuel is just uranium. It's no more radioactive than it was when you stuck it in. And it's not really a concern. And the fission products, they are very radioactive when they're created, but they decay rather quickly. They don't really have long-term radioactivity. They just decay too fast is the deal. There are a few of them that have very long half-lives, but that means their radioactivity levels are extremely low and they just don't really pose a hazard. The real challenge with spent fuel management is the presence of those transuranics, plutonium, americium, curium, because they have moderate half-lives and they have complicated decay chains. When you're looking at like a Yucca Mountain or a disposal site, what are we going to do with that? Well, the basic advantage of Lftr over that approach is we don't form those transuranics. We burn up essentially all of the fuel in this process because we don't remove fuel from the reactor until it's a fission product. General idea is you don't want uranium or thorium or anything else to end up in your waste stream, and that's a pretty straightforward proposition in this fluid-fueled reactor. So our waste story is a lot different. You can also then turn around and go back and take some of the waste that's already been created in our uranium-fueled reactors and potentially destroy those long-lived transuranics through fission. Waiting them out to decay is a very slow process. Plutonium-239, for instance, has a 24,000-year half-life, so that's a long time you're going to be waiting for that to decay. On the other hand, you can fission it, and then those fission products will decay very rapidly, and you also get an energy release and a neutron release, both of which are good. 1,000 kilograms of U-233, which is roughly what we've got. 90% of that will fission. We can make about $500–600 million in the electricity. Another $50 or $60 million on the fission of the uranium-235. Almost all of it will ultimately end up fissioning. Out of about 1,000 kilograms, about 15 kilograms of plutonium-238 will be left over. Now, this is good stuff. NASA is desperate for this stuff. Plutonium-238 is different than plutonium-239, the stuff we use in bombs. In fact, it's worthless for bombs. These radioisotope thermoelectric generators are based on plutonium-238, and this is the only way that we've been able to explore the outer solar system. The United States is unique, the only country in the world that has sent space probes beyond the asteroid belt. And it's all been based on having this technology. Short answer, we're out of the stuff. It's gone. We've used it all up. The Russians used to sell us some. They've sold us all their inventory. It's gone. NASA's got billions of dollars of deep space missions hinging on having enough of this stuff to run the batteries to let the thing call home. We will be able to make a reactor in Canada that is making home. We will be able to make this in Lftr. And it's worth It's worth almost as much as the stuff we burn up.
In addition, it would make medical molybdenum 99.
We are about to shut down the one reactor